¿Cómo me oyen? ¿Cómo? ¿Me oyen? ¿Me oyen?
Sí, señor profe, buenas tardes.
Yo, más.
Bien, señor.
Entonces, mm, ¿cómo les fue con los
Sí,
ejercicios? Sí, hola.
Bien, señor profe.
Ah, bueno, una preguntita acá con el micrófono. ¿Cómo se oye mejor? ¿Así
¿O cómo es la otra?
o así?
Como la primera.
¿Así se oye mejor?
Sí, señor.
¿Seguros?
Sí, pues yo lo escucho mejor, profe. No sé, mis compañeros.
Mejor dicho.
Como la primera, profe.
¿Así? ¿Así como está sonando? Estoy probando una vaina acá con manos libres, pues. Y así.
Profe, pues es que cambia muy poco el sonido, realmente.
Aguanten un momento.
Cambia.
No. ¿Me oyen ahora sí?
Sí, señor.
Bueno. Entonces hoy vamos a hacer trabajo suavecito. Entonces lo que quiero hacer es ¿cómo le hacemos? No, mejor como que lo comparto ya. Entonces les voy a poner un video para que sea suave para ustedes y para mí. Vamos a ver si corre.
About the difference between vectors and scalars, and they might sound like very complicated ideas, but we'll see over the course of the videos that they're actually very simple ideas. So first I'll give you a little bit of a definition, and then I'll give you a bunch of examples, and I think the
Vamos a hablar
examples
rápido
will
sobre
make things
vectores
super
y
clear. Hopefully
escalares.
they'll make things super clear. A vector is something that has a magnitude, or you could kind of view that as a size, and it has a direction. So and it has a direction.
Listo, primera pregunta. ¿Hasta ahí entienden?
Sí, señor.
Sí, señor.
Listo, un vector es un ente matemático. Necesita magnitud o tamaño y dirección.
And it has a direction. A scalar only has a magnitude or size.
El
And if
escalar
that
solo
doesn't make
necesita la
sense to
magnitud.
you, It will hopefully make sense to you in a second when I show you an example. For example, let's say that I have let's say that that's the ground right there. Let me do the ground in a more appropriate ground-like color. So this is green right over here. And let's say that I have a brick here. I have a brick on the ground. And I pick up that brick and I move it over to this place right over here. So I move the brick right over there, and then I take a ruler out and I say, wow, I've moved the brick. I have moved the brick 5 meters. I have moved the brick 5 meters. So my question to you is, my measurement of 5 meters, is it a vector or a scalar? Well, if I just tell you 5 meters, you just know the size of the movement. You just know the magnitude of the movement. So if someone were to just say 5 meters, this is a scalar quantity. Scalar quantity. And when we're referring to moving something, or how much something has, I guess, changed its position, and I don't give you the direction, we're talking about distance. And I'm assuming you've heard the word distance. How far of a distance has something traveled? So this is distance. So we could say that this block, or this brick, because of my picking it up and moving it, has moved a distance of 5 meters. But if I didn't show you this picture here and someone just told you that it moved a distance of 5 meters, you wouldn't know if it moved to the right 5 meters, you wouldn't know if it moved to the left 5 meters, if it moved up or down or in or out, or you don't know what direction it moved 5 meters. You just know it moved 5 meters. If you want to specify that, so we could say that this brick right over here, that it moved 5 meters to the 5 meters to the left. 5 meters to the left. Now we have specified a magnitude right over there. So that is a magnitude. And we have specified a direction to the left. So you now explicitly know that they went 5 meters to the, oh, sorry, it should be 5 meters to the right. Let me change that. So 5 meters to the, that's why the direction, to the right is what it got moved. It started here, it went 5 meters to the right. So once again, the magnitude is 5 meters, and the direction is to the right. So what I've just described to you right here is a vector quantity. So this, all of this business right over here, this is a vector. And when you talk about the movement, the change in position, and you give its direction, the vector version of distance, I guess you could call it, is displacement. So this right here is displacement.
Eso ya lo habíamos hablado. Cuando ustedes solamente dicen el número y las unidades, es la distancia. Cuando dan el número, las unidades y la dirección, es el desplazamiento. Ese fue el primer vector que aprendimos empezando este curso.
Displacement. So the correct thing to say, you would say that this brick has been displaced 5 meters to the right, or it has been moved a distance of 5 meters. Distance is a scalar quantity. I didn't tell you what direction we moved it in. Displacement is a vector quantity. We told you that it is to the right. Now let's explore this if we talk about the actual, well, we'll talk about the speed or velocity of something. So let's say that this 5 meters was traveled, and let's say that the change in time, and when let me just, because you're probably not familiar with what that means. So let's say that the change in time right here, change in time, when I moved this block 5 meters, let's say that it was, I don't know, let's say that the change in time was 2 seconds. So maybe right when the block started moving, maybe on my stopwatch it said 0, and then on my stopwatch when it stopped moving, it said, or when it got to this position, I should say, when it left from this position, my stopwatch said 0. When it got to this position, my stopwatch said 2 seconds. So the change in time, or the duration we're dealing with, is 2 seconds. And this is, for all we know, time only goes in the positive direction. So you could assume that it's, well, you could pick that as a vector or a scalar quantity, I guess, because there's only one direction for time, as far as we know, or at least in what we're going to deal with for the simple physics. So what's a measure of how fast this thing moved? So how fast did this thing move? So we could say it moved 5 meters in 2 seconds. So let me write this down. So it moved 5 meters. It moved 5 meters per 2 seconds. Per 2 seconds. Or we could write this as 5 halves of a meter per second. Or 5 divided by 2 is what? 5 divided by 2 is 2.5 meters per second. Meters per second. Meters per second. This right here is just the 5 divided by 2. Let me make that clear. That right there is just the 5 divided by the 2. So my question to you, this 2.5 meters per second tells you how far it traveled in a certain amount of time. Is this a vector or a scalar quantity? It is telling you how fast it went, but is it giving you just a size of this of how fast it went, or is it also giving you direction? Well, I don't see any direction here. So this is a scalar quantity. And the scalar quantity for how fast something is going, is speed. So we could say that the speed of the brick is 2.5 meters per second. Now, if we do the same calculation.
Vamos a pasar a otro. De hecho, un momento. Que esto corresponda a lo que yo quiero que ustedes aprendan. Entonces, vamos a mirar componentes.
Find the components of vector AB. So when they're talking about the components, at least in this context, they're talking about breaking it down into, if we start at point A and we're finishing at point B, how much do we have to move in the x direction? So this is going to be essentially our change in x. And then how much do we have to move in the y direction to go from point A to point B? So this one over here is going to be our change in x. I just wrote the Greek letter delta for change in x. And then the second component is going to be our change in y. And to think about that, let's just think about what our starting and final points are, our initial and our terminal point are. So this point right over here, point A, its coordinates are 4, 4. And then point B, its coordinates are, let's see, its x-coordinate is -7, -8. So let's first think about what our change in x is. And like always, I encourage you to pause the video and try to work through it on your own. Well, let's see. If we're starting at 4, and then we're going from x equals 4, that's where we're starting, to x equals -7. So that right over there is our change in x. And there's a couple of ways you could compute that. You could say, look, we finished at -7. We started at -4. You take your final point, or where you end up. So that's -7. And you subtract your initial point, -4, which is going to be equal to -11. The negative tells us that we decreased in x by 11. And you could see that if you could just visually count the squares. You could say, look, if I'm going from 4 to -7, I have to go down 4 just to get back to x equals 0, and then I have to go down another 7. So I have to go to the left 11 spaces. So that's -11. So that's my x component, -11. And what is my change in y? Well, I'm going from y equals 4. In fact, I'll start at this point right over here. I'm starting at y equals 4, and I'm ending up at y is equal to, let me do that in that other color. So I'm starting at y is equal to 4, and I'm ending up at y is equal to -8. So our change in y was going to be my final y value, which is -8, minus my initial y value, which is 4, minus 4, which is equal to -12. So -12. And you could see that here. If I'm starting up here, I have to go 4 down just to get back to the x-axis. Then I have to go down another 8. So I have to go down a total of 12. And you could see...
Preguntas. Si se dan cuenta que un vectorcito simplemente lo pueden descomponer en un par que está uno ubicado sobre el eje Y y el otro sobre el eje X. Entonces, si se dieron cuenta, lo que hizo fue delta X y el delta Y, o sea, punto final menos punto inicial, tanto para X como para Y. Esos son los cálculos, pero ustedes, ahí Irma les estaba diciendo, usted lo puede hacer contando. Acá tengo 4, 6, 8, 10, 11. Y si bajo, yo cuento 12. Entonces, cuando voy hacia la izquierda son negativos, cuando voy hacia abajo son negativos. Si voy hacia la derecha son positivos, si voy hacia arriba son positivos.
See something interesting that I've just set up here. You could also view this. You could view this bigger vector, vector AB, as being constructed of this x, this vector that goes purely in the x direction, and this vector that goes purely in the y direction. If you were to add this red vector to this blue-green, dark blue-green vector, you would get vector AB. But we'll talk more about that in future videos. We're asked which of the following vectors have the same x component as vector A, and they tell us to select all that apply. So this is vector A right over here, and we only have to concern ourselves with the x component. That's what they're asking us about. So let's think about what its x component is. We're starting at this point right over here, which has an x value of -2, and we're going from -2 to, or we're going from x equals -2 to x is equal to -5. So our change in x, or another way to think about it, our x component, we're going from -2 to -5. Our x value goes down by 3. So we have -3. We could say our change in x is equal to -3, or that would also be the x component of vector A. We could say that vector A is equal to, its x component is -3. We're not concerning ourselves with our y component, but we see that our y goes up by 1. So it's -3, 1. But we just care about our x component. So let's think about what other vectors here have an x component of -3, that if we start at our initial point and go to the terminal point, our x value has gone down by 3. Well, we're going to start with vector B here. And let's see, if we start there, our x value is 3 at our initial point, our starting point for that vector. And then to go to the x value of the terminal point, we went down by 3. So this has the same x component. Vector B is going to be -3, something. So I will select that one. Now let's think about vector C. Vector C starts here at x equals -4, and then it ends at x equals -1. So its x component is going to look, one way to think about it, our change in x is going to look like this. And you might be tempted to say this is the same thing. It has a length of 3, but notice we're not going 3 to the left the way that we did in vector A or in vector B. We're going 3 to the right. So here our change in x is +3. And so vector C is going to be +3, something. So it's not going to be vector C. Now let's look at vector D. Vector D starts over here. Its x value is -6. And we're going from x equals -6 to x equals -9. So once again, we have gone down. Our change in x is -3. So that has the same x component. If I were to say vector D, I would say it's -3, something. I haven't figured out what these are, but I don't need to for this problem. So vector D also has the same x component, an x component of -3. And we're done.
Listo, ¿preguntas hasta ahí?
No, señor.
No, señor.
Maravilloso. Entonces vamos a mirar estos. Una pregunta, ¿en alguna clase de matemáticas de las que están viendo o vieron el semestre pasado ya trataron el tema de vectores?
No que yo me acuerde, profe.
Entonces esto es totalmente nuevo para ustedes, ¿sí?
Sí, señor, creo que sí.
Listo. Entonces, el vector, ente matemático que necesita magnitud y dirección, se dibuja en el plano cartesiano como una flecha. El tamaño de la flecha corresponde a la magnitud, o sea, al número que le ponemos. Y la dirección, el ángulo con respecto al eje X, nos dice cuál es la dirección de ese vectorcito. ¿Listo? Pues ahorita miramos eso ya con tablero, pero sigamos mirando algunos de estos videos que son bastante educativos, porque la idea es hoy aprender a hacer o a mirar, pues, para qué nos sirven los vectores en la física. Hasta el momento nosotros solamente trabajamos una línea recta, de manera que nosotros decíamos la dirección es positiva o negativa. Esto nos va a servir para agregar más dimensiones.
We've already seen that a vector is defined by both its magnitude and its direction. And what I want to do in this video is get some practice calculating or figuring out the magnitudes of vectors. And I have a vector right over here, vector u. It is visually depicted here on our coordinate plane. And I want to figure out its magnitude. And I encourage you to pause the video and see if you can figure it out. Well, the magnitude of a vector, just the length of this line, you could view it as the distance between the initial point and the terminal point right over there. And so one way to think about it, you could view this, the magnitude of the vector, let me write this, the magnitude of the vector. Well, you could either think of it as the distance formula, which really just comes straight out of the Pythagorean theorem. It's going to be the square root of our change in x squared, change in x squared, plus change in y squared, plus change in y squared. Once again, this triangle, Greek letter delta, is just shorthand for change in y. And this once again comes straight out of the distance formula, which really comes out of the Pythagorean theorem. And it'll become a little bit more obvious when I draw the change in y and I draw the change in x on this diagram. So what's our change in y? Well, we're starting at our initial point, we're starting at y is equal to 9, and we are, to get to the y value of our terminal point, we're going down to y is equal to 2. So we have a change in y, our change in y is equal to, going from 9 to 2, our change in y is negative 7. Similarly, our change in x, we're going from x is equal to 2 to x is equal to 5. So our change in the horizontal direction is plus 3. So our change in x, or we could even think of this as the horizontal component of the vector, this is equal to positive 3. And as we've just seen, we have drawn a right triangle, and so we could use the Pythagorean theorem to figure out the length of the hypotenuse. And you might say, wait, a length of a side of a triangle can't have a negative value, and that's why these squareds are valuable, because it doesn't matter if you're taking a negative 7 squared or a positive 7 squared, you're going to get a positive value here. And if you really just view this as a triangle, all you care about is the length of this side right over here, or the magnitude of this side, or the absolute value of it, which is just going to be positive 7. And so we can say this is going to be equal to, the magnitude of our vector is going to be equal to, so 3 squared is 9, and then negative 7 squared is positive 49. So plus 49. Oh, once again, you could view this as our change in y squared, which is negative 7 squared. Or you could say, well, just look, the absolute value, the length of the side, we don't want to think of a side as having a negative value. The negative really just says, hey, we're going from the top to the bottom. It gives us our direction. But if we just say the length of it, it's 7. Well, there, if you just use the Pythagorean theorem, 7 squared would also be 49. And so either way, you get the magnitude of our vector is equal to the square root of 9 plus 49 is going to be 57. I don't think I can simplify this radical too much. No, that's it. So the magnitude of this vector is the square root of 57. Let's do some examples figuring out the magnitude of a vector if we're just given some information about it. So one of the simplest cases would be, well, if they just told us the actual components of the vector. So if they said vector A is equal to, let's say, 5 comma negative 3. This means that its x component is positive 5, its y component is negative 3. Well, if we have this, then the magnitude of A is just going to be, and this really just comes from the distance formula, which just comes from the Pythagorean theorem. The magnitude of A is just going to be the square root of the x component squared. So let me do that in a different color. So the square root of the x component squared, so 5 squared, plus the y component squared, so plus negative 3 squared. And this is going to be equal to the square root of 25 plus 9, which is equal to the square root of 34, which is equal to the square root of 34. And if you want to think about this visually, this is very easy to do just looking at the actual components. But if you want to make sense of this, why this is essentially just the Pythagorean theorem, we could draw out a quick coordinate axis right over here. So that's our y-axis. This is our, let's see, I have a y component of negative 3. So let's see, that is our, actually let me draw it a little bit different. Let me draw it like this. That is our x-axis. And we see its x component is positive 5. So 1, 2, 3, 4, 5. That's 5 there. And its y component is negative 3. So 1, 2, 3. And so this is negative 3. And so we can draw this vector with its initial point. Remember, we can always shift around a vector as long as we don't change its magnitude and its direction. We can start it at the origin and make it go 5 in the x direction and negative 3 in the y direction. And so its terminal point will be right over there at the point 5 comma negative 3. And so the vector will look like this. And if we want to figure out the magnitude, that's just the length of this line. And what we can do is just set up a right triangle where our change in y is this negative 3 right over here. That is our change in y, and our change in x is this positive 5. Is that positive 5? And so this is a right triangle. 5 squared plus, you could just view the absolute value of this side as 3. So 5 squared plus 3 squared is going to be the hypotenuse squared. It comes straight out of the Pythagorean theorem.
Listo, ¿dudas hasta ahí? ¿Ninguna duda? Súper.
Señor.
Entonces, seguimos armamos también tablerito. Sectores. Listo, entonces, vectores. Es un ente matemático definido, y esta palabra es importante, definido por magnitud. Esa magnitud puede que tenga unidades, como cuando dijimos la rapidez, 80 kilómetros por hora, y dirección. ¿Listo? Se representa por una flecha. ¿Cierto? El tamaño de la flecha nos dice la magnitud. Entonces, este tamaño sería la magnitud. Y voy a dibujar otro acá. Una dirección que generalmente está dada como el ángulo que hace con respecto al eje X. ¿Listo? Eso nos lleva a algo interesante. Eso nos lleva a algo que se llama sistemas de coordenadas. Entonces resulta que yo esa vaina, el vectorcito,
Profe,
yo lo puedo, dígame,
perdón, profe, ¿será que puede subir 5 un segundo?
claro que puedo subir 5
Un
y hasta
segundo.
6.
Listo, profe, muchas gracias. Ya,
¿Listo? ¿Alguien más o ya puedo bajar?
ya, profe.
Entonces resulta que yo puedo representar mi vector a partir de dos sistemas que son equivalentes. Yo puedo definir, por ejemplo, el estado civil de una persona como soltero o no casado, que son exactamente lo mismo. Entonces, esto sería Y, esto sería X. De la misma manera, yo puedo dibujar mi vector hablando del ángulo que forma y hablando de la magnitud. A esa magnitud yo la voy a llamar R, y yo normalmente la escribo así, no entre dobles rayas como estaban haciendo en los videos que ustedes estaban mirando. ¿Listo? No solo eso, acá en este punto, como vieron ustedes también, por el plano cartesiano yo puedo escribir la coordenada X y la coordenada Y, que corresponden a este punto donde termina la flecha de mi vector, y este sería entonces el origen o 0, 0, ¿cierto? Entonces resulta que hay una equivalencia entre los dos sistemas. Uno es hablar de la magnitud y del ángulo, o el otro es hablar del vector directamente en sus componentes horizontales y verticales, o sus componentes cartesianos. Entonces resulta lo que habían dicho en el video, de que nosotros podemos escribir este vector en términos de un vector que se dirige en la dirección X y otro en la dirección Y. Eso ya lo habíamos hecho. Y yo puedo relacionar los dos sistemas, o los dos sistemas de coordenadas, a través de el teorema de Pitágoras en este triangulito. Entonces, si ustedes miran, yo puedo definir el seno de teta como cateto adyacente. Entonces, este sería Y sobre la hipotenusa. Yo lo voy a llamar R así, sin carácter vectorial. También puedo definir el coseno como X sobre R, ¿no? Entonces ese sería cateto adyacente. Y además, de una vez, podemos definir la tangente como cateto opuesto sobre cateto adyacente. A partir de ahí yo puedo relacionar mis dos sistemas. Yo puedo decir entonces que la coordenada x del vector está dada por r seno de teta y puedo dar la coordenada y como r coseno de teta. ¿Listo? Entonces, estas dos me resultan bien importantes porque me sirven para ir de un lado al otro. Hay problemas en los que es más fácil dar las coordenadas x, y. Hay problemas en los que es más fácil trabajar con la magnitud del vector y el ángulo. ¿Listo? Entonces,
Profe, qué pena, ¿puede subir un poquito?
Regálame un segundo acá que me está escribiendo una profesora. Para que nos salga conveniente también vamos a usar esta, porque esta relación nos va a dar la dirección de nuestro vector. Y vamos a usar otra, que es la magnitud R dada como la raíz de x al cuadrado más y al cuadrado. En el video ustedes lo estaban viendo como delta x al cuadrado, delta y al cuadrado. Y eso sale del teorema de Pitágoras. Yo simplemente usé el teorema de Pitágoras, saqué raíz cuadrada a ambos lados y obtengo esta que me da la distancia entre dos puntos. Acá convenientemente la primera pareja de puntos está en el origen y la otra está en los puntos XY. Porque yo puedo tener otro tipo de vector. Por ejemplo, si mis puntos, ¿qué pasaría si mis puntos fueran un vector, o más bien, un vector que va desde el punto Q que tiene coordenadas menos 3,4 y otro punto que tiene coordenadas 5,3. ¿Cómo pintamos esa vaina? Entonces miremos, Qx menos 3, 1, 2 y 3, esto es menos 3 negativo, 4 en Y positivo, 1, 2, 3, 4, por acá, vamos a ver si es cierto. Entonces sería este punto. ¿Listo? Voy a escribir, esto es Y, esto es X. Ahora el punto P, entonces el punto Q, esto es menos 3,4. El punto P, ¿dónde estaría? 5 en X. Sería aquí 5 en X y 3 positivos. Entonces, sería 1, 2, 3. Aproximadamente por acá. Tenemos esto. Pues acá tendría yo otro punto que se llama 5,3. Y mi vector iría desde acá la cola hasta acá la cabeza. ¿Listo? Entonces, ahora la cuestión complicada es, bueno, ¿y usted cómo encuentra la dirección de eso? ¿Cómo encuentra la magnitud de eso? Entonces, ¿qué van a hacer ustedes? Van a hacerlo ya. Van a coger esta para la magnitud, van a coger esta y van a sacar o multiplicar ambos lados por arco tangente para encontrar el ángulo y me cuentan entonces qué les da.
Profe, no estoy seguro si es menos 0.64.
La magnitud.
Sí, señor.
La magnitud no le puede dar negativa nunca, hijo. Porque resulta que si usted tiene una raíz cuadrada de un número negativo cualquiera, esto le da imaginario. Y la magnitud de un vectorcito debe ser real. Entonces, por eso usted eleva al cuadrado y eso hace que si tiene, por ejemplo, menos 3 al cuadrado, le da menos por menos, le da más. 3 por 3, 9. ¿Y la pilla? Entonces, esta
Ah,
no
ok,
puede ser
ya,
real.
ya entendí.
Profe, me dio raíz de 53 en R.
Raíz de 53. Y
Sí, señor.
técnicamente con calculadora eso ¿cuánto le daría?
Más o menos 7,28.
Más o menos 7,27. Vamos a ver si el resto de compañeros les da el mismo valor.
A mí me
Profe,
dio
raíz
raíz de
de...
65
Sí, me dio lo mismo que a él.
y sería 8,06.
Sí, me da lo mismo.
Entonces miremos. Entonces habíamos dicho R, pero vamos a usar lo que vieron en el video, es delta X cuadrado más delta Y cuadrado. Esto, así nomás, es cuando el vector está puesto perfectamente, la colita en 0, 0 y la cabeza en los valores que sea. Entonces es obvio, sería final menos 0, que sería el inicial, y lo mismo acá, final menos 0, que sería el inicial. Pero en este caso, sí tenemos valores distintos, por eso toca ponerlo así. Entonces escribamos eso de forma explícita. Sería en X, ¿no? Final. 5
menos 3.
menos 3. Entonces cerrémoslo más bien acá con angular. Todo esto al cuadrado. Más. Final. 3 menos 4 al cuadrado. Entonces R sería igual 5 más 3, ¿sí? 5 cuadrado más, entonces esto da menos 1, ¿cierto? Al cuadrado, ¿cuánto da? 1 al cuadrado, ¿sí? ¿Estoy en lo correcto? 8 por 8, 64 más 1, igual raíz de 65, raíz cuadrada, ¿y eso cuánto da?
8,06.
8, bueno, lo podemos aproximar a 1, 8,1. ¿Listo? Ahora viene la otra cuestión. Vamos a usar este para encontrar cuál es el ángulo que hace este vectorcito con respecto al eje X. Bueno, entonces sería tangente de θ es igual a y delta y sobre delta x. De acá, si multiplico por el cotangente a ambos lados, me quedaría el ángulo es igual a la cotangente. En sus calculadoras aparece como tangente a la menos 1 de. Entonces, adentro, el delta x me da 8, ¿cierto? Adentro, el delta y me da menos 1. Cuéntenme cuánto da eso.
Menos 0.12,
Menos 0.12.
profe.
¿Alguien más le da otro valor? Revisen que la calculadora tenga grados y no radianes.
Menos 7,12, profe.
Menos 7,12.
Sí, menos 7,12.
Ah, ok. Entonces, menos 7,12. Y eso sí son grados. Entonces yo puedo hacer una vaina interesante. Voy a coger el rojo, efectivamente. Yo puedo coger este vector y trasladarlo acá. Aproximadamente, creo que queda así. Si ustedes lo miran, el vector es en magnitud idéntico y en dirección idéntica. ¿Qué fue lo único que yo hice? Moverlo al origen. ¿Para qué? Para que se pueda notar un poco más. ¿Qué cosa con esto? No, pero ¿por qué? Ahora sí. Para que se pueda notar un poquito más este angulito pequeño acá, que vale 7,1 grados, que fue el que a ustedes les dio. ¿Listo? Pero además de eso que yo acabo de hacer, me lleva a una vaina interesante, y es el hecho de que los vectores, a pesar de que ustedes los imaginen como muchos, los vectores tienen lo que podríamos llamar equivalentes. Entonces, podríamos hacer algo así. yo podría dibujar muchos vectores que se vieran de esta manera. Por ejemplo, así, si ustedes se fijan, todos, absolutamente todos, tienen el mismo ángulo con respecto a un eje horizontal y todos los tamaños de las flechas son igualitos. Eso quiere decir que todos estos vectores son el mismo vector, son este mismo vector, porque oficialmente, para hacer nuestras cosas más fáciles, nosotros ponemos los vectores con el inicio en el 0, 0 del plano cartesiano y la cabeza en el lugar donde nosotros pues tengamos dirigido el vector. O sea, todos estos, si yo lo cogiera cada uno y lo arrastrara hasta el origen, coincidirían con este que ya está ahí. Pues todos estos son el mismo vector. Bien diferente entonces, si de pronto yo lo que tengo es uno así. De pronto son parecidos en magnitud, pero fíjense que la cabeza apunta para otro lado. ¿Listo? Entonces yo podría borrar todos estos y decir, ah, el vector verdadero es este. Es algo así como imaginarse que Dios está en todas partes, creo que dicen. Entonces, realmente, todas partes es exactamente la misma parte, es exactamente el mismo Dios, digamos. ¿Listo? Eso nos sirve mucho para nuestros cálculos.
Profe, ¿puedes subir un segundo, por favor?
Puedo subir un segundo y bajar. Ahí.
Profe, gracias.
¿Listo? Entonces, para que esto siga siendo interactivo, vamos a seguir mirando videitos. Entonces vamos a ver vamos a ver cuando esto quiero arrancar. Por favor, me avisan si tiene sonido cuando empiece.
So let's get some practice and hopefully a little bit of intuition for adding and subtracting
señor, sí tienes ley.
two-dimensional vectors. So let's say that I have vector A, and let's say that its x component is, I don't know, 3, and its y component is -1. And let's say we also have a vector B, and let's say that its x component is 2, and let's say its y component is 3. Now let's first think about what would A plus B equal. So what resulting vector would this be? A plus B is equal to what? And I encourage you to pause the video and think about what this would be. Well, the convention is if we're taking the sum of two vectors, we can just add up their x components to get our new x component, and add up their y components to get the new y component. So the x component of vector A plus vector B is going to be 3 plus 2. That's going to be the x component, which we know is 5. And the y component is going to be -1 plus 3. -1 plus 3. And so the resulting vector is going to have an x component of 5 and a y component of -1 plus 3 is equal to 2.
Listo, breve. ¿Qué hicieron? Coja componente a componente y la suma. Pues la componente x de A y la componente x de B, 3 más 2. La componente y de A, que es -1, y la y de B, que es 3. Pues fíjense que de todos modos esta es una suma y esta es una resta, o una suma negativa. ¿Listo?
All right, that was pretty straightforward. Now, instead of adding them, let's think about what would happen if we subtract them. So let's think about what vector A minus vector B would be. And I suspect that you might be able to guess, or at least think about what would happen if you subtract vector B instead of adding vector B. Well, as you might have guessed, instead of adding the corresponding components, we subtract it. So our x component is going to be the x component of A minus the x component of B, because it's vector A minus vector B. So our x component is going to be 3 minus 2, 3 minus 2, and our y component is going to be the y component of A, -1, minus the y component of B, so -3. And so the resulting vector is going to be the vector 3 minus 2. The x component is going to be 1, and then the y component -1 minus 3 is -4. Now what I just showed you, this is the convention for adding and subtracting two-dimensional vectors like vectors A and B. Let's think a little bit about how we can visually depict what is going on. So let's first visually depict adding vector A and vector B. So let me draw some axes, and so this could be, there's my y-axis. Let's see, the highest y value I get to is, the highest y value I get to is 3, and the lowest is -4. And then so let me draw the x-axis someplace. Whoops, I didn't mean to do that. I did the zoom by accident. All right, so the x-axis, put it right over there. There's my x-axis. And let's see, the highest x value is 5, the lowest is 3. Actually, I could just focus on the, let me just focus on the right-hand side. So that's y, and then let me do x looking like that, x-axis. And now let's see, vector A is 3, -1. So 1, 2, 3, and -1. If we want to just visualize it in standard form, we could put its initial point at the origin and its terminal point at the point 3, -1. And so we could draw it like that. We could also shift it around as long as it has the same, magnitude and direction. We could shift it around. So that right there is our vector A. Now vector B, 2, 3, we could have its initial point at the origin and we could draw it like this. So the x-coordinate is 2, y-coordinate 1, 2, 3. So its terminal point could be there. So we could just draw it like this for vector b. But if we're going to add vector b to vector a, like we have right over there, what we want to do is shift vector b over so that its, I guess you could say, tail starts at a's head, or its initial point starts at a's terminal point. So let's do that. So if we start right over here, we're going to go 2 in the x direction. So we're going to go 2 more in the x direction, and we're going to go 3 in the y direction. So 1, 2, 3. So we're going to end up right over there. So notice, this is the same vector, vector b. I've just shifted it over. Has the same magnitude and same direction as what I had drawn before. As
si se pillan que él inicialmente lo pinta desde el origen y luego lo corre acá. Entonces está haciendo uso de lo que yo les conté de los vectores que son equivalentes. Y el cuento gráficamente es, primero se pone el primero que aparece en la suma y luego en la cabeza del primero se pone el inicio del segundo, por eso lo está poniendo acá.
Is that vector right over there, I have just shifted it down and to the right. And now when we do this, so this is vector A, I'm adding vector B, I put the initial point of vector B at the terminal point of vector A. I've shifted it over right over there. So now I can figure out the resulting vector A plus B, the resulting vector A plus B, by going from the initial point of A to the terminal point of B. So it's going to start here and then go over there. And notice, this vector, I'm going 5 in the x direction and 2 in the y direction. This is the vector 5, 2, right over there. That is vector A plus vector B. Now let's think about what happens when we do A minus B. Well, we could still have vector A just like we drew it, but now instead of putting vector B's tail or initial point at the terminal point of vector A, we would want to put negative B. So negative B would just have the same magnitude, but it would be in the opposite direction. So instead of going 2 to the right and 3 up, we would go 2 to the left and 3 down. So just 2 to the left and 1, 2, 3 down, and we would end up right about there. And so if you subtract A minus B, that's the same thing as A plus negative B. So negative B is going to look something like this. It's going to be the exact opposite direction. It's going to look like that. And so there, if you start at the initial point of A and get to the terminal point of the negative B now, this is all hand drawn, so it could be a little bit more precise. Notice, we get to the point 1, negative 4. 1, negative 4. So this vector right over here, let me do that in a different color. This brown, whoops, that's not what I wanted to do. This brown vector right over here, that is the vector A minus B. And then this white one, actually let me do this in another color as well. This magenta vector right here, that is A plus B. So hopefully that makes sense. And if you, given the components, if you're adding the vectors, add the corresponding components. If you're subtracting the vectors, well, if you're subtracting B from A, subtract B's corresponding components from the corresponding components of A.
Listo, ahora vamos a ver eso gráficamente.
Let's build our intuition for visually adding and subtracting vectors. So let's say that I have vector A, and I add that to vector B, and the resulting vector is vector C. So what could this look like visually if we assume that A, B, and C are two-dimensional vectors? Well, I'm just going to draw what vector A might look like. So let's say that this right over here is vector A. And vector B, since I'm adding it to vector A, I'm going to put its initial point at the terminal point of vector A, and then I'm going to draw vector B. So let's say vector B looks like that. So that is vector B. So let me label these. That is vector A. This is vector B. And I did that so that I could figure out what the sum is, what vector C is going to be. So that is vector B. And what would that be? Well, we would start at the initial point of vector A and then go to the terminal point of vector B. So this right over there would be the sum. So that would be vector C right over there. So the important realization is if I add two vectors, I would put the tail of one at the head of the other. And now what's neat about this, if I'm adding, the order doesn't matter. I could have done this the other way around. I could have started with vector B. I could have said vector B plus vector A is equal to vector C is equal to vector C. And you could see that visually. It would be a slightly different visual diagram, but you get to the same place. So if I start with vector B, let's say I start over here. Let's say that that's, in fact, you don't have to start at the origin, but let's say that was the origin. So I could start with vector B, draw vector B just like that, and then add vector A to it. So start vector A at the terminal point of vector B, and then go to, and then just draw vector A. So vector A. So once again, a vector, I can shift them around as long as I'm not changing the direction or their magnitude. So vector A looks like that. And notice, if you now go start at the initial point of B and go to the terminal point of A, you still get vector C. So that's why A plus B and B plus A are going to give you the same thing. Now what if instead of saying A plus B, I wanted to think about what A minus B is going to be. So let me write that down. Vector A minus vector B. Minus vector B. And let's call that vector D. That is equal to vector D. So once again, I could start with vector A, and here order matters. So vector A looked something like this. This is hand-drawn, so it's not going to be completely perfect. So vector A, just like that. And it's one way of thinking about subtracting vector B is instead of adding vector B the way we did here, we could add negative B. So negative B would have the same magnitude, but just the opposite direction. So that's vector A. Vector negative B, we'll still start it right over here, but we'll go in the opposite direction. So let's do that. So negative B is going to look like this. It is going to look something like this. So that is negative B. Notice, same magnitude, exactly opposite direction. We flipped it around 180 degrees, and now the resulting vector is going to be D. So vector D is going to look like that. Vector D. So C is A plus B, D is A minus B, or you could even call this A plus negative B. Now with that out of the way, let's draw some diagrams and go the other way. See if we could go from the diagrams to the actual equations. So let's start with, let me draw an interesting one. So let's say that this, well, let's say that's vector A. Vector A. Let's say that, I'll use green. Let's say that that is vector B. And I will now use magenta. And let's say that this is vector C. Vector C. So I encourage you to pause the video and see if you can write an equation that defines this relationship. Well, this is interesting because they're all going in a circle right over here. You could start at, let's say that you started at this as your initial point. You said, okay, A plus B. Well, if you're trying to figure out what A plus B is going to be, the resulting vector would start here and end here. But vector C is going in the opposite direction. But we could, instead of thinking of
Listo. Nos queda solo escalar. Entonces resulta que también
About
podemos
vector C,
multiplicar.
what I want to do in this video is give ourselves some practice.
Podemos multiplicar un vector por un número escalar, sea que tenga o no unidades.
And hopefully some intuition on multiplying a scalar times a vector. Now, what am I talking about when I say multiplying a scalar times a vector? Well, let me set up a little two-dimensional vector here. So let's say I have the vector W, and let me give it an x component. Let's say its x component is 1, and its y component is, let's say it's 2. And I could draw it if I like. Actually, that's a good idea. It's always nice to be able to visualize these things. Let me get some coordinate, get a coordinate axis here. So that's my x-axis. That is my y-axis. And so if I were to draw this vector in kind of standard form, I would put its initial point at the origin, and then its terminal point would be at the point 1, comma 2. So its x-coordinate is 1. Its y-coordinate is going to be 2. So 1, 2, this vector is going to look like, its initial point is right here, its terminal point is going to be right over there. The vector in standard, graphing it in standard form or visualizing a standard form would look like that. Now, of course, I could have the same vector and I could shift it around as long as I have the same length of the arrow and it's pointing in the same direction. But if, no one tells you otherwise, it's nice to just put its initial point at the origin. Now let's multiply it by a scalar. Now what do we mean by a scalar? Well, a vector is something that has a magnitude and a direction. A scalar is just something that has a magnitude. You could think of just the numbers that you started learning when you were 4 years old, that those are scalars. So for example, we can think about what is 3 times W going to be? 3 times W. 3 is a scalar, W is a vector. Now the convention we use for multiplying a scalar times a vector is you just multiply each of the components times that scalar. So this is going to be equal to, we have a 1 and a 2, and we're going to multiply each of those times the 3. 3 times 1, and then 3 times 2, and so this is going to be equal to, 3 times 1 is 3, 3 times 2 is 6. And so we see the resulting vector, 3, we could call this vector 3w, or it's going to have an x component of 3 and a y component of 6. So if I were to draw it in standard form here, x component 1, 2, 3, and then y component 2, 3, 4, 5, and 6. And so it's going to look like this. Let me see if I can draw it reasonably. It's going to look like this. And obviously I'm hand drawing it, so it's not going to be exactly right, but it's going to look like that. So this is the vector 3 times W. Now notice what happened when I multiplied it by the scalar. The direction didn't change, but the magnitude did. And you see what the magnitude changed by. It increased by a factor of 3. This was the length of my blue arrow now is 3 times the length of my magenta arrow. Let's do another example. And I'll use the same vector W since we already have it set up. Let's multiply it times a negative scalar.
Hay alguno afuera. No aparece. No, pues me dejó funcionar acá el Chrome. Mentira, no funciona. Sin embargo, ya no hay tiempo, entonces les voy a dar el link de Khan Academy para que revisen lo que quieran revisar, lo que quieran repasar. En la siguiente clase, pues hacemos algunos ejercicios al respecto. Esta vez sí en una clase común, corriente y menos entretenida, porque voy a estar hablando solamente yo. Yo ya les mando eso. De momento, ¿les quedó alguna duda de lo que vimos?
No, señor.
Es breve, ¿sí o no?
Sí, señor, es breve.
Listo, la cuestión es que nosotros vamos a estar usando vectores en todo. Entonces aparece el desplazamiento es un vector, la velocidad es un vector, la aceleración es un vector, la aceleración de la gravedad es un vector, la fuerza es un vector, el momento lineal es un vector y más temas que van a ver ustedes después. No me quiere funcionar el WhatsApp. Entonces, en vista de eso, ya explotamos, nos falta solamente una parte que es la caída libre, que también se realiza en una línea recta, y de resto todo es en 2 o 3 o las 3 dimensiones. Entonces ya a partir de ese punto tenemos que trabajar conociendo un poco sobre los vectores y el álgebra vectorial, que es simplemente la suma, la multiplicación, la resta, todo eso. ¿Listo? Todavía nos faltan un par de cosas, pero pues ya se acabó el tiempo. Entonces, por hoy dejemos así. Ya les mando el link para que revisen lo que quieran sobre eso. Y pueden revisar obviamente también los libros de física que hay en el CRAI. ¿Listo?
Listo, profe.
Bueno,
Hola, profe, gracias.
Que sean felices y que me piensen. Nos vemos el miércoles.
Listo, profe, gracias. Buena tarde.
Una pregunta.
Señor.
¿Qué es lo del taller ese que toca subir a látex? ¿Qué va a pasar con él?
¿Ya lo subí a látex?
Ya, profe.
¿Y para cuándo se solicitó?
No, profe, ni
No,
idea.
pues me dijo que hoy revisáramos lo que no pudimos meter en látex.
El laboratorio, profe.
Entonces
Sí.
hagamos una cosa, el día miércoles, cuando empecemos, me recuerdan que tenemos que hacer esa revisión y miramos eso en bombas, ¿les parece?
Listo, profe. Excelente.
Perfecto. Gracias, profe.
Listo. Igual si tienen dudas entre hoy y mañana, pues me pueden preguntar por el WhatsApp.
Listo.
Profe,
Una señorita quería hablar.
Diego.
Bueno, si no hay nada más que decirnos, entonces que sean felices. Chao, chao.
Chao, profe.
Chao, profe, gracias.
Chao, profe.
Chao.
Chao, profe, gracias.
Vemos.